Dear students, in the last class we have discussed the transport phenomena and also viscosity. Okay. So, here according to kinetic theory of gases, the molecules of a gas are in a state of thermal agitation. Okay. So, to attain a stable state or equilibrium state by transporting momentum and heat and also mass from one layer of a gas to the another layer, which give rise to the viscosity, conductivity and diffusion respectively, and the phenomena, this phenomenon is called as the transport phenomena. Okay. So, here the gas molecules to attain a stable state or equilibrium state. So, from why? Because here the gas is in the form of layers. Okay. So, here to attain the stability, stable state or equilibrium state, some physical quantities like the momentum, heat and mass, these transfer from one layer to the another layer. Okay. So, here this phenomenon is called as the transport phenomena. Okay, ma. So, now so we have already discussed viscosity, which is the transport of momentum. Now we will discuss the thermal conductivity. Okay. So, thermal conductivity can be attained by the transport of thermal energy. Okay. So, here the viscosity is attained by the transport of momentum. Okay. So, now the thermal conductivity can be attained by the transport of thermal energy. Okay. So, now yes. So, now here we already know that the gas which consists of different layers and each layer has a unique temperature. Okay, that is the different layers have different temperatures. Okay. So, here the molecules will carry kinetic energy from regions of higher temperature to the regions of the lower temperature to bring about an equilibrium state. Okay. So, here we will consider a fixed mass of gas which is at rest as shown in this figure. Pen I want. Yes. So, here in this figure we have this is a gas which some mass of gas which is at rest. Okay. Suppose here there is a uniform temperature gradient, that is temperature gradient is d theta by dz. So, this is temperature gradient we are taking on the z axis, that is d theta by dz. Okay. So, and also here the gas molecules which are moving along the x axis. Okay. So, now here this the center one, that is AB is the center layer and the temperature of this layer is center layer is theta. Okay. So, now here above AB and below AB the layers are there. So, above AB the layer is EF and below AB the layer is CD. Okay. So, now the temperature of the above layer, that is EF layer, is equal to theta plus lambda into d theta by dz. Okay. So, here we have this lambda is the mean free path. Okay. So, now the temperature of the layer EF is equal to theta plus lambda into temperature gradient, that is d theta by dz. Similarly, the temperature of the layer CD is equal to theta minus lambda into d theta by dz. So, now these are the temperatures of the layer EF and CD layer. Okay, so now here we have suppose so here we know that some of the gas molecules which move from the upper layer to the lower layer, that is from EF layer to the CD layer through the layer AB. Similarly, the molecules which move from the CD layer through AB to the EF layer. Okay, so here the suppose the number of molecules crossing unit area of the layer upward or downward. Okay, so upward or downward is NC by 6. Yes. So here NC by 6 is the number of molecules crossing the layer, that is unit area of the layer, either upward or downward, per second is NC by 6. Okay, so here N is the number of gas molecules per unit volume and C is the average molecular velocity. Okay, so suppose if M, let us consider the small m is the mass of each gas molecule. Okay, so if we consider mass of each gas molecule, then the mass of M molecules which are crossing the layer AB upward or downward is equal to M into NC by 6. ఓకే, సో ఇక్కడ మనం ఏమనుకుంటున్నాము, ఒక యూనిట్ ఏరియా, సపోజ్ మనం ఒక యూనిట్ ఏరియాని తీసుకున్నట్లయితే ఒక లేయర్లో ఇఫ్ యూ కన్సిడర్ యూనిట్ ఏరియా, ఆ యూనిట్ ఏరియా నుంచి ఒక సెకండ్లో ఐదర్ అప్వర్డ్ ఆర్ డౌన్వర్డ్ డైరెక్షన్లో మనకి ఎన్ని మాలిక్యూల్స్ క్రాస్ అవుతున్నాయి అనేసి మనం తీసుకున్నట్లయితే అది ఎన్నవుతాయి, NC by 6 మాలిక్యూల్స్. ఓకే అమ్మా, సో సపోజ్ ఇక్కడ మనం ఇఫ్ వీ కన్సిడర్ the mass of each gas molecule, so here M is the mass of each gas molecule, then M molecules, n number of M the molecules which are having the M mass are crossing per second either upward or downward direction can be written as M into NC by 6. Okay, so now here we have so now let us consider the specific heat at constant volume. So here CV is the specific heat at constant volume. Then the heat energy carried out by the molecules in crossing unit area of the layer AB in the downward direction per second can be written as that is heat energy means Q. Okay, so Q is equal to mass into specific heat into temperature. Okay na, so identidi manaki suppose manam CV is the specific heat, okay, at constant volume, and mass of each molecule is M, and then the molecules which are crossing through this layer AB is equal to Mn into MnC by 6. Okay, and also the temperature of the top layer, the upper layer of AB, that is EF layer is equal to theta plus lambda plus d theta by dz. ఓకే, సో ఇప్పుడు మనం ఏం రాస్తున్నామంటే ఇక్కడ హియర్ వీఆర్ రైటింగ్ ద ఈక్వేషన్ ఫర్ ద హీట్. ఓకే, హీట్ ఎనర్జీ ఎంత ఉంది, ఈఎఫ్ లేయర్ నుంచి మనకి ఈ కొన్ని మాలిక్యూల్స్ మనము కింద లేయర్కి రావడానికి ఎంత హీట్ ఎనర్జీ రిలీజ్ అవుతుంది అనేసి అంటే దట్ ఈస్ ఈక్వల్ టు Q is equal to mass into specific heat into temperature. Okay, so mass is MnC by 6 and temperature specific heat is CV and temperature is theta plus lambda into d theta by dz. Okay, so similarly the number of molecules, the heat is carried by the molecules in crossing unit area of the layer AB in the upward direction. Okay, upward direction is Q is equal to mass, that is Mnc by 6 into specific heat is Cv into temperature is theta minus lambda into d theta by dz. Okay, now so here the equation 1 is moving downwards. Okay, the heat energy carried out the molecules moving downwards. Okay, so here equation 2 is the heat energy carried out by the molecules to cross the layer along to the upward direction. Okay, so now we can write the net. We can write the equation for the net. Okay, so the net transfer of heat energy, now we can write. Okay, so the net transfer of heat energy is that is equal to Q is equal to equation 1 minus equation 2. Okay, so if we write if we solve equation 1 minus equation 2, then we get this equation. Okay, so that is Q is equal to 1 by 3 Mnc into Cv lambda into d theta by dz. Okay, so here in this equation we have this Mn. Mn is the density of the gas. So we know rho is equal to the density. Okay, so put rho is equal to m into L. Okay, so in this equation, then we get the net the net transfer of heat energy Q is equal to 1 by 3 rho C lambda into Cv into d theta by dz. Okay, so now here this give the number, equation number, it would be 3. Okay, so now we know that the coefficient of thermal conductivity. Okay, so we represent the coefficient of thermal conductivity with the symbol K, and the coefficient of thermal conductivity can be defined as the quantity of heat that flows per unit area per second per unit temperature gradient. Okay, so that means we can write the coefficient of thermal conductivity K is equal to the thermal conductivity can be written as Q is equal to K into d theta by dz. Okay, so now this one. So now these equations, that is equation 4 and equation 3 are the equations for the heat. Okay, so now that's why we can compare these two equations. So we equate these two equations, then we get K into d theta by dz is equal to 1 by 3 into rho into C into lambda into Cv into d theta by dz. So by simplifying this, we get K is equal to 1 by 3 into rho into C into lambda into Cv. Okay, so this is the equation for the thermal conductivity, coefficient of thermal conductivity. Okay, so now what happened? Yes. So now this is the equation for the coefficient of thermal conductivity. Okay, so here this coefficient of thermal conductivity. So here thermal conductivity is the transport of thermal energy gives the thermal conductivity. Here this thermal conductivity is that is to attain the thermal conductivity equilibrium. So here the transport of thermal energy should be there. Okay, so finally we write the equation for the thermal conductivity, that is coefficient of thermal conductivity K. Okay, now here we can find out what is the relation between the coefficient of viscosity and the coefficient of thermal conductivity. Okay, so in the last class we have derived the coefficient of viscosity. Okay, eta. So that is eta is equal to 1 by 3 rho C into lambda. Okay, now just now we derived the coefficient of thermal conductivity K value. So, K is equal to 1 by 3 rho C lambda into Cv. Okay, so here from these two equations we get the K is equal to eta into Cv. Okay, so that is the coefficient of thermal conductivity is Cv times the coefficient of viscosity. Okay, here, but this equation holds good if all the heat supplied is converted into kinetic energy, then only this equation holds good, that is K is equal to eta into Cv. Okay, so here, so every time the supplied heat energy is not converted into kinetic energy. So, we have to correct this equation. Okay, so we have to modify this equation. So, the modified equation is, that is the corrected equation is that corrected equation is given by Champman and Enscoge. Okay, so these two persons they corrected this equation. So, the corrected value is K is equal to, so the corrected value is, so here we have K is equal to eta into Cv. Okay, so now the corrected value is equal to K is equal to some epsilon eta into Cv. So, this epsilon is the value of epsilon is equal to 1 by 4 into 9 gamma minus 5. So, here we know that this gamma is the ratio of two specific heats. Okay, so now our K, that is the coefficient of thermal conductivity K, can be written as 1 by 3 into epsilon into rho into C into lambda into Cv. Okay, so this holds good for all the that is for all the temperatures. Okay, so this is all about the coefficient of thermal conductivity, and this is the relation between the coefficient of thermal conductivity and the viscosity. Okay, so now we have and also here we can find out the effect of temperature on the coefficient of thermal conductivity. Okay, so here we have the coefficient of thermal conductivity is proportional to the root of temperature. Okay, root of absolute temperature. Okay, so which means the coefficient of thermal conductivity is directly proportional to the square root of the absolute temperature. Okay, so in other words, the coefficient of thermal conductivity increases with increase of temperature. Okay, so similarly, the effect of pressure on the coefficient of thermal conductivity. So, here also the coefficient of thermal conductivity is independent of the pressure. Okay, so as the coefficient of viscosity is independent of pressure, similarly here the coefficient of thermal conductivity is also independent of pressure. Okay, so thank you.